University. His research interests include robotics, virtual reality, sensor fusion, planning algorithms, and so forth. With regard to industry, he was an early founder and the chief scientist of Oculus VR, acquired by Facebook for a whopping $3 billion in 2024, advisor to startups in robotics and virtual reality. And most important of all, he has been our professor for XR, and anyone over here would have attended his curriculum here. So I give a very warm welcome to Professor Steve LaValle, and I ask him to raise the stage.
So today I've decided to give about a 1-hour talk in 20 minutes. So I'll just give a kind of a sampler of like tasting all the food kind of quickly. So from virtual reality and perception engineering, this is where I work most of the time, University of OULU. That's kind of how it looks right now at about noon. It's dark and cold and snowy, so just like Chennai. So a little bit of Oculus background. So the Oculus work that I did was mainly in OULU, but at the time I was a professor at the University of Illinois on sabbatical. I'm American. I lived there for 50 years and then got bored and moved to Finland. So quickly I got disrupted development for the Oculus Rift, mainly the head tracking and calibration things. There's me speaking at Oculus. It's Palmer Luckey sitting on the floor and some others in the company in the earliest days. I think I'm explaining magnetic fields and calibration and stuff like that. There's a book about all of this if you're interested in popular books and such that covers my story and the more important stories of Palmer and lots of other people. So going back, just reflecting on this, and something that will set the tone for my talk. So when we were working on the original Oculus Rift, it was just a 3-degree of freedom tracking system, so just trying to track which way your head's moving, because you have to present the graphics with the right viewpoint at the right time. So you need a sensor to do that. So one of the first things my wife and I did was develop the basic core math library for the Oculus Rift, including the quaternion algebra and such, and then made a very simple angular velocity integrator that would estimate where the head is using that. And I can tell you, at the time you do an online search and you find lots of crummy class projects that can kind of halfway do it for you, but they don't work very well at like a consumer product level. And I remember arguing with people. Now it would be you ask ChatGPT to write the code, and I assure you it will not be high quality. It will probably have kinematic singularities and other things that take a lot of time to learn in very difficult kinds of classes at places like IIT. So one of the first things that happen is drift error. So over time the error accumulates, and then you have to use other sensors to align with respect to a field. Latency is a huge problem. So when I turn my head, it's the stuff in the right place at the right time. And it's not only latency, but we later learned it's a kind of spatio-temporal accuracy that has to be aligned with human perception. And that stuff I'll get into in a bit. But I wanted to mention I worked on predictive tracking and made a very simple predictive tracker.
On behalf of all of you, I would request Steve to take more time in explaining this now his plenary talk, because this is what we are all assembled for. And also the other chief guest, Ms. Divya Innocent IAS, is unwell and she's not giving a plenary talk. Therefore, I would request, since this is more interesting, you take more time in explaining things and make it. We are all very interested. We are here.
I'm psychologically prepared to go very fast. But it's one of the things I love about the culture here. There's always room for last-minute adjustments, I think. So I've learned that very much from my wonderful times here. So basically, we're trying to do predictive tracking. One very simple thing. If your head is turning at some rate, and you're measuring that, then one of the troubles is that it takes a long time to go back and compute the graphics, everything from that viewpoint. So that takes some amount of delay. So it's helpful to predict. So I hacked up something very simple, did some simple prediction, and it was working pretty well. And then I talked to some experts from VR who had done research back in the 1990s before that. And they said, well, it's a double-edged sword. Sometimes it works well, sometimes it doesn't if the prediction's bad. But what was interesting was that the prediction intervals were different from the 90s to 2012. In the 90s, that's the upper diagram there, you would have maybe one measurement every, say, 16.67 milliseconds, and then you have to predict maybe 100 milliseconds into the future because everything was slower, the sensors and the technology. But for the system we had, which was very low cost, we had a 1,000 hertz gyroscope, and then we only had to predict about 30 milliseconds into the future. And so the thing that was different, and I like to say that on the order of about 20 milliseconds, you have no free will with regard to your head. It's going to keep going in the direction it was going because of momentum. So the physics tends to dominate. Not true for fingers so much, but for your head, you're going to injure yourself if your head rotates too quickly. So that enables us to make a very good predictor for that. And so I started making better predictors using angular acceleration and other things like that. I used my knowledge of science and math and engineering to make something better. And I did an experiment like this where I turned my head back and forth and measured the angular error. Blue is with no prediction, which is a dumb thing to do, but that's what they were doing before. And then red is this very simple extrapolating angular velocity. And then the yellow one was something I spent a couple of weeks on, I was really proud of, and it was better in terms of worst case error and average case error. I gave it to one of my colleagues, Peter Geocaris, who was very sensitive for visual things, and he said it's worse. So I said, come on, I did the math, I did the studies, it's better. Come on, the numbers say it's better. He says, well, it's worse. If you just hold your head still, my new method was kind of jittery. It was kind of shaky in some ways. And so this was a perceptual problem. So it turns out the more you try to predict, as you try to reduce latency, you make things more brittle. In the other direction, if you add latency, you can smooth things and make them go in the other direction. So it's kind of like anti-smoothing. That's just stock market data there, but it behaves the same way. So it all looks kind of the same. So we ended up doing perception-based filtering inside the company, and that was the only kind of idea patent of the company at the time. So the idea was that when your head is stationary, it does more smoothing, and when you turn your head, then it smoothly transitions into doing some prediction. Because when you're turning, you don't notice, but when your head stops, when you're stationary, you don't notice latency. But when you turn and then your head stops, if the things are not in the right place, they're very tightly integrating with humans at a very low level. And so I became very interested in perceptual psychology and human physiology, neuroscience, all these kinds of things at the time. Motor skills, all these kinds of things become very important. So there are all these factors coming up. I ended up hiring a couple of perceptual psychologists, and we got very rigorous in our approach to try to handle these kinds of problems, and it still goes on today. So since that time, I've seen the industry struggle quite a bit. This is something I remember from the 1980s, 2015 or 16. Now it's back down at some level, but it's still a much higher level than it was back in the 90s and these things. And one of the reasons why it continues to thrive and move forward, even in spite of the ups and downs, one of them is that the component technology keeps getting better. So when you have new components, in the Oculus case, we had components from the smartphone industry. We had IMU, the inertial measurement unit, we had GPUs, the display. So just taking a cheap lens and shuffling all these things around brought us very close to, let's say, a new level of VR technology or XR technology that was not possible in the 90s. So for much lower cost, we were able to do that. But then what do you do now? The industry's stuck on very, very challenging nanophotonics, optical engineering problems. So these are really, really hard problems. And it's hardcore applied physics. Who knows what's possible in the physical world, right? I mean, you have to really know what you're doing. It's like as if you're imagining semiconductors coming along from 1940, you know, and you have your vacuum tubes and things like that. How do you know what kind of things there's going to be in the future? So it's very hard to know these things. So there was this big consumer product revolution, but it kind of went back down again when it became clear that you cannot do much with the component technology other than just big, heavy headsets on your face with optical systems and things like this that are, you know, simple lenses. They improve the lenses, they improve the number of things, but the weight is very heavy, and it's ultimately not the greatest solution to just take your video display technology and just strap it to your face. It needs to be completely redesigned based on human perception. I loved this article back around 2015 when it came out from The Economist. What will be the killer app? We're still looking for the killer app, but the phrase killer app is also flawed because that comes from the smartphone industry. It's not going to be like a killer app. It's going to be something else. You have to find the use cases. They could be, they may vary. So even the phrase killer app is suspicious. And that leads me to the next point, which is that we're always recycling. So I think industry is recycling. Okay, academics are also recycling. This is the bad kind of recycling, by the way. There's a good kind of recycling, which is throwing your bottles in the right place. But this kind of recycling is, if you're in a company and you have a very powerful technology that you've spent 20 years on, maybe more than that, and so many billions of dollars of investment, you're going to want to use that and adapt it a little bit to make the next product. But the trouble in this XR technology is that it's not just a simple adaptation. It will take you somewhere, but it will not take you all the way. So you'll be stuck, and then you have to go back to the first principles and start over again, and that requires massive investment and a lot of innovation. And that's frightening. I don't blame a company for not wanting to just say, okay, let's stop everything we're doing, spend 10 years now in massive investment on something else, because the company will not exist in 10 years after doing that, right? unless they have a huge amount of extra cash for investment, like Meta is doing right now, some other very large companies are doing. But it's a very high risk move. So these are the kind of things we see. I've already said the hardware has been recycled. I've already said that the software is the same thing. Like for example, if you use a game engine like Unity or Unreal Engine for VR development, it does not take too long before all of your experiences look like first-person shooter games, because that's what it was developed for. And they're doing a lot to make it more adapted to XR and things like this, but that's where it comes from. So it's just ecology, so vision science and these kinds of things. It's getting better, but very rarely is anyone integrating that into the entire design process at all levels. That's what needs to be done. It's not like, oh, I'll build this really cool engineered device, and then I'll just look okay. Can we ask some people? Oh yeah, okay, no, sort of okay, you know, fine. But if you had designed it at all, if you integrated this mentality and the scientific knowledge at all levels, then it gets much better. And I don't even want to go into all the problems of recycling the operating system. You also need new operating system concepts and things all at the level of computer. And this will be true in any operating system or anything you design. And it's interesting because there's a great parallel, because you have to figure out what the human would sense if they were in such a virtual world and turning and moving in certain ways and such. And so there ends up being great parallels between, say, the human vestibular organ, because it's in the same physical world and on the same scale, roughly. Let me talk about what perception engineering is. Secret drink down here. So if I were able to convince you that I'm here talking to you today, but then all of a sudden it's a surprise, and it's really Professor Moneyvan who's talking all this time, that would be an illusion. So what is perception engineering? I come from an engineering background. I've worked over 30 years in engineering. My PhD is in electrical engineering, so I think of myself mainly as an engineering type. And so if you look at these different areas of engineering historically, you're taking the sciences and applying the learned principles in order to construct things in the physical world that hopefully benefit society, sometimes harm society. It's challenging to bring that in for perception engineering because there's a reverse engineering part, which is the organisms like us, we did not design ourselves. So scientists have to spend time poking in, prodding in, doing all kinds of experiments to understand what's going on here. Just doing basic measurements is very challenging. So I see this whole thing, XR technology, as being an example of a very powerful example of perception engineering. You might think that Finland, I had a chance to meet the Indian ambassador to Finland, Mr. Kumar, and he said that after I gave him a VR presentation, he said, what about social media? Is that an example of VR? And it kind of stuck in my head. I'm like, yeah, why not? It fits pretty well. So it may be higher level, but a lot of the same kinds of principles are there. So people are delivering perceptual illusions, and maybe they're able to win elections and do other kinds of things like this by manipulating people's perceptions of truth and reality. So what's really hard? So it's really hard for these, going back to reverse engineering in the red part here, it's very hard to measure what's going on in the system. So we have ways we can measure what's going on in the device, so we can take measurements from the humans by asking them questions. But if you have a model of what you're trying to do, then you go and implement it, make a prototype, proof of concept, get some data from it, and see if you need to update the model. It's behaving like you predicted. So it's very hard to do that when we did not engineer ourselves. So one thing I'm running in OULU is a big European research project. It's a very prestigious project. It lasts for 5 years, and it's on the VR, XR, kind of interchangeably, to a more established engineering discipline. I've noticed that people outside of the field think that maybe they're in another field of engineering, and then they look at XR and say, oh, it's just a bunch of fancy technology and business, but nothing really scientifically unique or a general view. We want to have a kind of grand theory of VR or general VR. But what's weird about it is we have one branch of that applied to organisms and another branch that we apply to robots. That's not a ridiculous question, is it? I mean, at least in the robot case, we fully engineered. We should understand what's going on inside. Assuming we didn't put too many dumb black boxes in. But if we really fully engineered the whole thing, we should know what's going on. Convince it to give it a perceptual illusion that it's done cleaning the floor, because it thinks the wall is somewhere where it's not. So Marco is like a virtual reality display for that robot. And it's perfectly consistent and logical, and you can give a good mathematical account of these things, and you can ask questions of somebody else's robot, or can I do better testing for my own robot? So this is very important. This kind of thing does go on in autonomous driving in the automotive industry, for example. People are doing these kind of things all the time. The car, but they may not put the wheels on, other things, they may just have some pieces there, and the rest just doing communication between the electronics as if it were real. And and do a lot of testing like that. So very similar, I think that's VR for robots. These are important because they can fully analyze these things. So after a lot of work in our group, we came up with a kind of definition of what perception engineering is. And this could work as a definition of VR, XR, whatever you like. Let's take a look at this. So we have two different kinds of agents. I use the word agents to mean a biological or engineered system, a robot or a human or a dog or anything you want, or an IIT Madras monkey. And I'm not sure they all approve, but let's see. Okay, so we have an agent which can be biological or engineered, and there's two of them. There's a producer and a receiver. Okay, the producer alters the environment with intent. It's not accidental. It's engineering, so there's intent. We don't usually do oops, I accidentally built a bridge. You know, it's not like that. It's engineering is with intent. So you alter the environment. You alter the environment with the. That's why we put some adjectives like X or V or whatever. I don't care which ones you want to use. Some kind of different nonsensical reality. Right, so that's basically the idea. And again, I don't know how many more R's we need and X's. It doesn't matter. And I also kind of think about artistic paintings, photography, motion pictures, and again, disinformation on social media. They can all be considered as examples of this. So what is perception? Well, it's largely invisible to us. We're perceiving things all day long without being directly aware of it. This is where an artist very cleverly did some things to make this look three-dimensional. You perceive it as being three-dimensional, but why is that? You think that's a little person there? Or a faraway person, right? So you perceive it as a faraway person. There's a kind of texture gradient here from the tiles. The buildings have some kind of slightly weird, but some kind of perspective there. So you have enough things. These are all cues. And when you put them together, there's a kind of illusion of a three-dimensional scene here. However, we still know that that's not a three-dimensional scene, really, because we understand what paintings are. Maybe if you showed someone a painting like that for the first time, things where you're just changing a bunch, you're flashing a bunch of images, let's say. Which line is longer? I'm just going to flip through this. This one's really bizarre if you haven't seen it. This A and B square are exactly the same pixel values. Do you believe that? It's crazy, right? So what's going on there? So people create these things. There's the famous dress illusion. I don't think it's really an illusion. People just argue about what the colors are. Is it a rapid and curved and everything and extended? So they did all kinds of tricks here. This one's really wild. That's a perfectly square rectangular grid, but it looks curvy. And this one, if you're sitting close enough to it, looks like it's breathing. If you're far away, it probably doesn't, but there's no motion there. So again, going back to picture, just an old philosophical point here. This says in French, this is not a pipe, but it's a picture of a pipe. So if you have to, whatever theory you make, you have to differentiate these kinds of things out. And again, I imagine what people 100,000 years ago, mathematical modeling, and we have a kind of God's perspective looking down on the system so we can do mathematical analysis. I just want to say that we've mathematically formalized these two notions, plausibility and illusion. And basically it says the perceptual experience or the percept is plausible if there's just some reasonable interpretation, let's say. There's some possible interpretation. It's very intuitive. I've skipped the math. I just want to assure you that there is some math underneath this. But the idea is that there's some plausible explanation for what's going on. It's something believable. If not, then you just kind of have a panic and nothing really works. Like a very broken virtual reality headset. You know, you're like, this doesn't make any sense at all. I turn my head left and the world goes right or something. It doesn't make any sense. So it has to be plausible. And then it has to be an illusion, which basically means that the thing you're perceiving and the thing that is happening in the external world do not correspond perfectly. It does not correspond to reality. In fact, they're happening. This one we cannot take measurements because color perception is something very internal. There's no kind of agreed upon thing. We all perceive colors differently, so this ends up with a bunch of people arguing. And this one really depends how you want to resolve the philosophical conundrum of whether or not you say this is actually a pipe or just a picture of a pipe. So you can define things sort of either way. And then there's multi-stable perception, which occurs as a dynamical system over time. Things change, so you have multiple perceptions. What's the front of the cube or the back here? Or is that a duck or a rabbit? You can make yourself probably see both of them. So again, I have a little more mathematical stuff. I wanted to skip over this a little bit and just say that there's a whole theory of pre-images that we have. And let me give a very simple example. Suppose you're out in a field, you're out on the plain, maybe you're out on the campus somewhere, and there's a tower transmitting a signal. But here, we change the signal intensity of tower 2, and we end up weakening the signal intensity so that you end up believing that you're further away. So that's a perfectly reasonable, very easy to understand, purely engineered illusion, and I think this corresponds to perception engineering. And then you have a lot of interesting questions of under what right. But if you only have 2 towers instead of 3 towers, then you have a range of possible values of intensity with which you can fool a person. You can make them think they're in a certain location and such. So we've started developing a whole kind of, let's say, control theory or control theoretic version of these things where we can manipulate sensors and maybe vehicles and make them think they're going somewhere and actually cause them to go where we want them to go. Right? So that can be done with purely with this kind of theory and such. Sounds a bit evil, right? So, but you can also say you can make your device robust so that no one can do that to you. So it depends on how you want to look at it. And this fits with humans as well. There's these ideas of that we develop called robust illusions then. And you see this in virtual reality. Sometimes some of the illusions are very robust, sometimes they're very brittle. Sometimes you have, that's different than the agent viewpoint, with the agent is being fooled, the receiver. It's very important to keep these separated. It took us a very long time, some years of thinking about it, to be very careful about these boundaries. We don't assume that the agent has the God's viewpoint. The God's viewpoint is looking down on everything. This is very close to models in neuroscience, such as, for instance, free energy principles. So you see a very simple kind of coupled dynamical system model. And a lot of our mathematical theory is based on game theory, going back to the work of von Neumann and others, going back to the 1940s. We use the notion of information spaces. This is before Claude Shannon. So Claude Shannon did wonderful work on information theory, entropy, and so forth. This is before that. And in this case, it has to do with playing games with imperfect information, like a battleship game or something, where you don't know where the pieces are. Final thing about it, which is, do the gods who are doing the analysis know the inner workings of the agent that's being fooled? In the case of engineering, we can make a kind of white box, let's say, where we know everything that's inside, or a clear box, if you like. But in the case of humans, it's more like a black box. But I would say it's a little bit of a gray box because in front of us. So we're trying to control these things and analyze these humans while much of the system remains a black box. There's still a lot of great mysteries of what's going on in the human perceptual system and motor control system, motor cortex, and many other things going on. So that's the kind of situation that we face. We do work in our group on applied work as well as some of these things, like panoramic tele and medical and assembly operations and things like that. To get to the end here, I think there's a great abundance of transformative applications in this area. I explained why industry struggles, and I think there's this emerging discipline of perception engineering that's going to take a very long time to figure out. But I tried to give you some kind of guideline, and the theory will help guide us, I think, of where to look, help predict outcomes, provide explanations and analysis. So to really wrap up, understanding of human perception, motor control, and physiology is critical and should be integrated into all stages of development. If you want to push India into being the XR corridor by the 2040s and so forth, then these are the things to really focus on. And I think IIT Madras, the great universities in India, can do a great job developing this in research and in teaching and education. Free book, and here's a paper about the mathematical things that I skipped.